Okay, so for the first week, I think I mentioned on Tuesday that the attendance policy has changed for SPC. We used to take attendance for the first 2 weeks. Now it's just the first week, which I think is a little dicey because, for an online class, I have most of our due dates for Thursday, and nothing's due the first week because we're just getting started. So your first, real graded assessment, credit quiz one, isn't due until Thursday next week. What I try to do is we're going to basically do a chapter every week. Every Tuesday, Thursday, we'll be working on a chapter. And then I'd like to give you a week to prepare to take the credit quiz. So that means going through your notes, going through the homework, practice worksheets, whatever's in the folder to keep you practicing the material. And then the credit quiz is due a week after we finish the actual chapter. So we're going to finish chapter one tonight, which means the credit quiz one is due a week from tonight. So next Thursday at 11:59 p.m. However, we have to report attendance for the first week by Tuesday of next week. So what I did, normally the practice quizzes are going to be due the entire semester, but what I've done here is I've made that practice quiz one A, because there's A, B, and C, so just A. I'm going to use this for attendance purposes. So I've put that in the syllabus. It's also noted in the folder, but I'm going to send an email out tonight as well that just because of this attendance that I have to do the first week, I've made practice quiz 1A actually have a due date of Sunday at midnight. So if you could just, if nothing else, make sure that that quiz is taken care of. You don't even have to do well on it. I just need you to submit something. So I know that you are active in the course. The practice quizzes you can take as many times as you want. So even if you just go in and submit it, then that means, okay, you're active in the class. And then you can take it again when you have more time, whatever it is. But I just have to do that this first week. Sorry, I know it's kind of an inconvenience, and I don't like that they changed the attendance policy. 2 weeks is much better. I've got plenty of time to make sure that someone's actually not in the class, but 1 week is kind of hard. But anyway, those are the only two due dates, excuse me, coming up this week ahead. So tonight our job is to finish chapter one. Next week we'll start chapter two. If you start looking ahead into the chapter two folder, you're going to see that I've got chapters 2 and 3 in the same folder, and it's because I just didn't like the way Tro organizes the chapters. So if you remember Intro Chem, when we do mass, mole, atom, molecule conversions, if it's an element, we have atoms, right? But if it's a compound, we use molecules. He separated them. He was like, well, let's do the elements in this first chapter, and then let's do molecules in the second chapter. But it's the same calculation. So I kind of thought that was sort of strange. So I make a long story short, I kind of reorganized chapters 2 and 3, but because of that, I had to just sort of lump it into one folder because that's how it's going to appear in the textbook. So anyway, if you're looking around and a little bit confused why it's organized that way, that's why. All right, so with that said, we can finally get started with what we've got to do tonight. So I always like to recap. For chapter one, a lot of this you probably saw before in intro. You probably remember it. We looked at classifying matter. We talked about elements, compounds, and mixtures, and how elements and compounds are both considered pure substances because they have constant composition. For example, every sample of carbon dioxide gas should look exactly the same. It's a carbon center, two oxygens double bonded on either side at a 180-degree bond angle, but they all look the same. Mixtures are when we take elements and compounds and mix them together. And because they're just mixed sort of how we design them to be mixed, the composition is variable. And that's how we know that they're not one pure substance, right? They're a mixture of multiple substances. So a lot of times the term pure substance throws students because they're thinking, a lot of times we hear pure and we think about, oh, it's clean. It doesn't have any yucky stuff in it, right? Like if we're thinking about food or cosmetics or something like that. To a chemist, pure means that you just have one substance in that sample. So it's not a mixture of anything. It's pure. It's one thing. Like it's just H2O, right? So pure in chemistry means a little bit different than what we're probably used to in terms of hearing it with regard to like food or cosmetics is another one. Okay, so homogeneous is when that mixture, all those components in the mixture come together really, really well and it looks uniform throughout. Heterogeneous is when it doesn't come together very well. Oil and water is the classic example. They do not mix well because they have differences in polarity. So that makes a heterogeneous mixture. So that's where we started. Then we looked at chemical and physical changes. This is going to be your first lab for the coming week. A physical change, really, when I was learning this, I thought, well, it's just a phase change, right? That's like the simplest example, and it always works. So if we're looking at dissolving salt, that's the equation that I've got for you up there, right? Dissolving is just a physical process. We could get the salt back if we wanted to. We could evaporate off the water. Any kind of phase change, evaporation, or what's called sublimation when dry ice, when you use that at Halloween, when it sublimates into the fog, the CO2 gas, that is just a phase change. We're not changing the molecular structure. We're not breaking any bonds or forming any new bonds. So that's always a physical change. A chemical change is a chemical reaction. So these are, of course, much more interesting, but that's when we actually go in and break bonds and then form new bonds. So what you'll notice is in the reaction, the product side and the reactant side, they look different because you have new substances that are formed. Now, properties just describe the matter. So we're not looking at changes, we're just describing. And a physical property just describes the matter without doing anything to it. We're just like looking at a sample and it's right there in a jar and we're trying to say, okay, what color is it? What does it smell like? What texture? Is it a solid, liquid, gas, right? Those are all physical properties. We're not doing anything to it. A chemical property describes what happens to the matter when we start messing with it. So maybe we add other matter to it, like we combine a different substance, we mix it together, we see what happens. Or maybe we just light it on fire or try to and see what happens. Those are chemical properties, right? It describes the chemistry that like new matter being formed or maybe not being formed if no reaction occurs, but we're definitely messing with the matter. We're doing something to it when we're explaining what happens. All of these things, these properties are used to distinguish between matter. All right, and then we went through some examples. Then we talked a little bit about energy, endothermic and exothermic. I think I mentioned we've got chapter 7 a few weeks obviously from now, but we're going to go in great detail into energy. Endothermic is when heat flows into the reaction. That's how I remembered it. So it's absorbed from the surroundings and it goes in to either breaking bonds or whatever is happening in terms of the phase change, breaking intermolecular forces. So that energy is sucked up by the process. And then what happens is the surroundings gets cold because imagine you're dissolving a salt in water and it's an endothermic process. That salt is sucking up energy in order to dissolve. And so those surrounding water molecules are giving their energy to that dissolving process. And because they've lost energy, they slow down because now they're tired, right? And temperature is just molecular movement. So if they're slow, the temperature drops, right? So that's endothermic. Exothermic's the opposite. Heat exits, right? So you can have salts that are endothermic when they dissolve, you can have some that are exothermic. So a salt that is exothermic as it dissolves, it will release energy to the surroundings. The surrounding water molecules take up that energy and start moving faster. And when they do that, the temperature shows us that the temperature goes up. So kinetic energy, energy of movement. Potential energy is an energy of position. Classic example in physics is like holding the ball 6 feet in the air, right? It has potential energy. We'll worry about that more in a molecular, kind of situation in terms of chemistry later when we get there. Thermal energy, I always thought thermal temperature, right? So thermal energy is associated with the temperature of an object, which, as I mentioned, temperature is a measure of molecular movement. So really it's an indirect kinetic energy, form of kinetic energy. So that was a lot of conceptual stuff, right? Now it's time to get into the math. So we looked at the MKS system. This is our standard system. And by ours, I mean almost everybody but the United States. And so we are not on the metric system. So we have to learn how to get our units to match the metric system. So what we started with were prefixes. Now, this doesn't really have anything to do with going back and forth because you can use prefixes on the SI standard system or you can use it on our English system. Like we can say we've got kilopounds. We hardly ever do, but we could. Or we could say we have, instead of meters, we could do inches. We could have centi-inches. All right. I've never heard anybody do that, but you could, right? It's the prefix you can apply to any base unit. So we practiced that I know always there's a question of what exactly do I need to memorize for test one. I did put in the exam review folder, there's a file that says T1 for test one, 2045 for our class, memorize. So you'll find on that sheet, if you open it from chapter one, these are the 6 conversion factors I need you to remember. There are others. We don't need to know those. These are the 6. Those are the 6 I want you to know. Anything else I would give you. Nano is going to become important when we do the energy chapter, actually chapter 8 after that. When we start looking at wavelengths. Micro, we might use a little bit, but milli and centi, you probably remember from intro, we use those quite a bit, as well as kilo, and mega we'll probably use a little bit. All right, so then we talked about proper scientific notation. And proper scientific notation always means that the decimal has to follow the first non-zero digit. So all of these are in proper scientific notation. So what I mean by that is, if I wrote, just as an example, 25.26 times 10 to the 2, that is not proper scientific notation. Proper scientific notation would be to go ahead and move that decimal all the way to follow the first non-zero digit. So we got to move it 1 spot to the left. We would make it 2.526. Since we moved it to the left 1 spot, we have to add 1 to the current exponent. So 1 to the left, right? We talked about if you go left, you're adding. So adding 1, so 2 would become 3. All right. And it bothers me to not have a unit because any scientist would say you always have to have a unit. So I'm just going to arbitrarily put grams on here. But my main point was to talk about proper scientific notation. So proper scientific notation, yes, these two numbers mean the same thing, but in proper scientific notation, we always want the decimal to follow the first non-zero digit. So there's only one number before the decimal. So we looked at what these exponents mean in terms of the prefix, right? 10 to the negative 6 is micro, 10 to the third is kilo, -9 nano, -2 centi. That's all we were doing there. Then we started practicing that proper scientific notation like we just looked at. And then we kind of pulled everything together in that last example. All right, now density. We know density from intro, if not even from sooner than that. Before that, we know density is mass divided by volume. And then what we talked about on the next page is, okay, well, how do we find the density of a solid versus a liquid? All right, and so if you have a solid, and this is something we're going to practice in lab, not next week, but the week after, you're going to have an aluminum bar, and then you're also going to have a glass sphere. The aluminum bar, it's a prism. So you'll be able to find the length, width, and height in centimeters using the ruler. And then you multiply those 3 together and you can find the volume. So that is if it is a regularly shaped solid, right? We can measure length, width, and height. The glass sphere, we can't do that. So we're going to use the displacement of water method. And this one, I think you're familiar with. You start with your graduated cylinder with a certain amount of water in it. When you put the sphere in, the water level is going to go up. However much water moved out of the way must be the volume that's occupied by the solid. So the example we did was, okay, we started with 15.6 milliliters of water in the cylinder. We put the solid in, water level goes up to 25.0. What's our density? Well, we found the mass of that glass sphere first. And then the difference in those two volume measurements tells us the volume that was occupied by the sphere. Now, we're going to talk more about significant figures tonight, but whenever you do subtraction or addition, but in this case, subtraction, you want to follow the decimal place. So the least decimal places always wins. Now, both of these are the same. 1 place past, 1 place past. We keep it 1 place past. We lost a sig fig, though. We went 3 sig figs minus 3 sig figs and ended up with 2. But with addition subtraction, you're not worried about sig figs. You're worried about how far past the decimal can I measure. So this device we were using, the graduated cylinder, could only measure to the 10th place. That's how it's calibrated, right? That we can't get any more data than that. So I couldn't tell you what was past the 10th place for my answer because I'm not able to measure that. So all I can do is, since both of those two measurements go 1 place past the decimal, my answer has to go 1 place past the decimal. So our subtraction, we found our volume, our difference of 9.4. Now we do the division, mass divided by volume. Now we look at sig figs. 4 sig fig mass, 2 sig fig volume. So we have to round to only 2 sig figs for the density. Least always wins. Significant figures, the idea is, in math, we didn't worry about this at all. But in chemistry, the idea is when we give our answer, we also want to express what we know, how accurate the answer to be, right? How precise do we know it to be? Accuracy is a little different, but so it depends on the devices that we used in our measurements, right? If we have really good, precise equipment, then we're going to be able to get more sig figs. We'll have more precision. But if we've got equipment that isn't calibrated to be very precise, then our answer can't be very precise. Kind of makes sense. All right, now for a liquid, we're going to do the density of water. And instead of using a graduated cylinder in lab, we're actually going to use a burette. But the idea is pretty much the same. The volume we're going to measure by the container using the meniscus. The mass we're going to get by difference. How much liquid did we add? Okay, so that's the mass. We'll do a mass measurement empty versus with the water. The difference there gives us the mass of the water. And the volume can come from the meniscus level, reading the volume. So that's what we did here. We did the subtraction first, the difference to find the mass of liquid added, divided it by the volume, and then we got our density. So the rules with significant figures, the 0 is the only problem digit. If it's not a 0, it's automatically significant. So anything that's not a 0 is a sig fig. It's a measured digit. The zeros are problematic when I find for students, when they're either in the front or at the end. In the middle, students always remember they're significant. It makes sense, right? If I can measure the 1 and the 5, I can measure the 0 in 105. I didn't put 115, right? It was 105. So I clearly measured that 0. When the zeros are in the front, the way I had to train my brain to think about it was, if I put some, whatever it is, a penny or whatever it is on the scale, and it gives me 0.0067. Anyway, it doesn't matter. But anyway, let's say that's my mass measurement. The first thing that registers on the scale, right? The first thing that's actually measurable is the 6. The zeros, there's nothing there. So it's not really measured. It's just magnitude. That's it. There's nothing yet to measure until we get to the 6. So the leading zeros that come before the first non-zero digit, those are never significant figures. They're just placeholders. The zeros at the end, so different books have different rules for this, but this is the rule I've always used. I think it works just fine. The zeros after the last non-zero digit, they are significant as long as there's a decimal written in. So 20.0, those 2 zeros are after the 2. There's a decimal there, 3 sig figs. 250, no decimal, 0 at the end. What that says to me is that is an estimate. It's about 250. So only the 2 and 5 would be significant figures. However, some textbooks will say, you know what, that's really ambiguous. Let's just use scientific notation because that's going to make it really clear. And honestly, sometimes you get in a little bit of a bind and you have to use scientific notation. So just as an example, let's say I had 100.42 was my answer. But whatever I did to get there, I needed to round it to only have 2 significant figures. All right, well, that's going to be a little bit of a problem because if I take my 1, that's my first sig fig, the 0 would then be my second sig fig. What I'm kind of cutting off in terms of it has to be now at this point rounded. It's not going to round the 0 up to 1, right? The 0 is going to stay a 0 because the rule is whatever you're cutting off, if it's 5 or greater, the previous digit rounds up. If it's 4 or less, the previous digit stays the same. So if I just put this as 1, 0, that's not good, right? Number 1, it only has 1 sig fig. If you think, well, I'll put the decimal, I just lost magnitude. I went from 100 down to 10. That doesn't work either. So that's not going to work. If I keep it as 100, right, because that's at least the right number, without a decimal, that's 1 sig fig. But with a decimal, that's 3 sig figs. So that's also not going to work. So the only thing we can do for this one, and again, it rarely happens, but sometimes it does. So you kind of have to be prepared just in case you might have to use scientific notation. And that is the benefit of scientific notation. It makes the sig figs perfectly clear. There's no ambiguity when you've got scientific notation. So I'm moving my decimal 1, 2 spots to the left. So it's a positive 2 on the power. And I'm just going to keep 1.0. There's my 2 sig figs. And of course, because I'm a scientist, I got to put the unit on there. All right. So that is the benefit. Oops, sorry. That is the benefit of scientific notation, is that whatever it gives you in scientific notation, that is the correct number of sig figs. So if I say you've got 1.050 times 10 to the 3 milliliters, I don't even have to look. I just look right here. 1, 2, 3, 4, right? So that is 4 significant figures. I don't even worry about the exponent because those are just placeholders. I just look, whatever's written there, that's how many sig figs we have. So definitely the nice part of scientific notation. All right, so now we're caught up to where we left off. We're going to look at addition, subtraction. We already talked about this. The rule with addition, subtraction is always follow the least decimal places of everything that you're adding or subtracting together. When you multiply or divide, this one I think is easier. We just follow the least number of sig figs. So typically what I find is the multiplication division rule does not cause any trouble. It's the addition and subtraction rule that is so easy to forget. So I've got this first example here in our practice. I've got 48.2 plus 3.82 plus 48.4394. And I went ahead and got the answer on the calculator. All right. So what I would do is, rather than doing this first, is I would go through and I'd say, okay, my 48.2 goes to 1 decimal place, 3.82, 2 decimal places, 48.4394, 4 decimal places. So my least, right? Least always wins. I got to go just 1 decimal place. So I'm going to take my answer that I got from the calculator and I need to stop at just 1 decimal place. So that 4 in the tens place, that's my last digit. So what I'm cutting off, right? I'm cutting off a 5. I don't look anything past the 5. I just look at that very first digit that I'm cutting off. Because it's 5 or greater, that means that my previous digit is going to have to round up. All right. So we're going to round that previous digit up. So the 4 is going to become a 5. So what I'm going to have for my final answer is 100.5, right? And that would be my final answer in meters. The other way you can think about it is when you set it up this way, this is how I did it when we were doing the density calculation, looking at the displacement for water, for the volume. If I look at my first measurement of 48.2, whatever device I was using, my assumption is it could not read for me anything past the tenths place, because if it could have, I would have written it down, right? If I knew it was a 0, I should have put that there. But whatever device I was using, if it only went to the tenths place, what that tells me is that I wasn't able to measure anything past that. So same thing with the 3.82, right? Couldn't measure anything past that. So the idea is that when you get your answer after addition and subtraction, you can only go as far as you know the numbers, right? So like we don't have anything past the tenths place in that first measurement. So that's why we can't say with confidence anything of after the tenths place. I don't really know that 5 in the hundreds place is a 5 because I don't know what was there in the first measurement. So that's why we always round to like the least number of decimal places if all we're doing is addition or subtraction. So the next one I've got here is 148 plus 2.39 grams plus 0.0124 grams. Okay, so what I'm looking at here is the 148 doesn't have any decimal places. So I'm just going to put 0 dp. The 2.39 has 2 decimal places, and the 0.0124 goes 4 decimal places. Least always wins, right? So I've got to go 0 decimal places. So in other words, I've got to stop right at the ones place. Now what I'm cutting off is 4 or less. So that means that 0 needs to just stay a 0. I'm going to round it down to 150. Now I got to be careful. If I just put 150, without a decimal, I'm saying that that 0 is not a significant figure, but we want it to be significant. So that's why we're going to make sure and put the decimal. If you prefer the scientific notation, definitely feel free to use that, but you're not required. I think the decimal rule makes total sense to me. So I like using it, but if you prefer the scientific notation, do that. Another example, it's all we're doing here is addition, subtraction. So same rule all the way through. So we've got first measurement 15.436 that has 3 decimal places, 5.3, just 1, 6.24 has 2, and 8.177 has 3. So I plugged everything in, got my answer on the calculator. The rule is we look at least decimal places. The 5.3 is going to limit us to only 1 decimal place. So we're going to have to stop at 6.3. Can't go anything past that. Okay. So next one though, now what we've got is an addition in parentheses, a subtraction in parentheses, and then multiply those two together. And order of operations would say always do what's in the parentheses first. So looking at those two operations in the parentheses, one is addition, one is subtraction. So the rule is decimal places. So 51.5 has 1 decimal place. 2.67 obviously has 2. So that first answer for the parentheses, I'm going to cut it to the tenths place. So I stopped at 54.2. In the second parentheses, I've got a 2 decimal place value minus a 3 decimal place value. So my answer can only go 2 decimal places. So I stop at 33.30. When I multiply those two together, now I'm going to shift gears because now it's a new rule. So normally when you're doing calculations, if all you're doing is adding and subtracting, like we were for questions A, B, and C, you do all of it in the calculator, you round it at the end. But if you have D, like we're doing in part D here, a change in operations, we add, we subtract, then we multiply, then you really have to round at each step appropriately so that you get the answer with the right number of either sig figs or decimal places, depending on what you're doing. So the first job when we added or subtracted, we followed the decimal place rule. And then now that we're going to multiply, we're going to shift and start thinking about sig figs. So 54.2 has 3 sig figs. 33.30 has 4 sig figs. When I multiply those together, least sig figs wins. So I'd go to 3 sig figs. So if I had 1,804.86, rounding to 3 sig figs, that's one of those scenarios where we just talked about, you have to use scientific notation. Because 1804.86 to go to 3 sig figs, I would need the 1, 8, and the 0. So I can't do 1800 because that's only 2 sig figs. I can't do 1804 because that's 4 sig figs. So the only way I can do this is 1.80 times 10 to the 3, because then there's my 3 sig figs, the 1.80. Those are my 3 sig figs. All right. So last one here, or sorry, there's 2 more as an example. All right, I've got 125.1 minus 1.22. So I'm looking at my decimal place rule. So when I plug this in the calculator, that answer gives me 123.88. But I can only have 1 decimal place for my answer to that subtraction. So I'm going to round that to 123.9. All right. Then in the other parentheses, I've got 52.5 added to 0.63. Calculator gives me 53.13. All right. But if you have 52.5 with only 1 decimal place, my answer here can only have 1 decimal place. So we're going to round that to 53.1. All right, so we got our answers to the 2 parentheses. Now we can do the division. So I'm going to take 123.9 grams, divide it by 53.1 milliliters. And now what I need to think about is significant figures. So 123.9 has 4, 53.1 has 3. So least wins, we're going to go with 3 sig figs. So we're going to go 2.33, and then the units there don't cancel out. It would just be density, grams per milliliter. So a question just came up in the chat. Question was 33.30 meters. Why is that 4 significant figures? The reason is that the 0 that comes after the last non-zero digit, the rule is it is significant as long as there's a decimal present anywhere in the value. So zeros at the end are significant as long as there's a decimal written in. All right, and it doesn't matter where that decimal is. So that has 4 significant figures, 33.30. If this was 3,330 without a decimal, and there's now the 0 at the end and there's no decimal present, now we're looking at something that's only 3 significant figures. All right, so it's the fact that there's a decimal there that makes that 0 a sig fig. Oh yeah, all right, one more example here. So we're doing, in parentheses, we've got a subtraction. We're gonna take 47.5 minus 1.44. My calculator gives me 46.06. But when I did that subtraction, I need to think about decimal places. So that 47.5 only has 1 decimal place. So that's the least or lesser. So I need to do the same for my answer here. So I got to round it to the tens place. So 46.06 is going to round to 46.1. All right. Then in the parentheses, I've got 10.5 meters times 0.35 meters times 0.175 meters. And that answer, when I'm multiplying, I look at sig figs, but let me get you the answer first. Calculator gave me 0.643125. Units are like x in algebra. If I take x times x times x, I get x cubed. Meters times meters times meters gives me meters cubed. All right. And when I look at my sig figs, 10.5 has 3. 0.35 only has 2. 0.175 only has 3. So the 0.35 is going to limit our answer here to 2 sig figs. So my answer from that multiplication is 0.64 meter cubed. All right, so now I've got the answers from the 2 parentheses. Now I can do the final answer. So I'll take 46.1 kilograms and divide it by 0.64 meters cubed. And because I'm doing now division, I want to think about significant figures. And the 0.64 only has 2 sig figs. So my answer is going to round to 2 sig figs. And what I get is 72. And the unit there would be kilograms per meter cubed because the units, it's another density unit. They didn't cancel out. All right. So with operations, you just have to make sure and pay attention to which rule are you following. Addition, subtraction, look at decimal places, multiply or divide, make sure you look at significant figures. All right. And if you've got both operations, then you have to really go at each step appropriately. So we'll practice more of this. But next, on the next page, we have a discussion of precision versus accuracy. All right. So the classic example they always use is playing darts. And the assumption is that when you play darts, you want a bullseye. So person comes up and they're playing darts. And so I'm not going to be able to draw this very well, but there's my bullseye, and sort of here's my dartboard. There's my doubles and my triples. So first person comes up, hits the bullseye, which is good. Then if it were me, maybe even doesn't hit the doesn't hit the dartboard at all, and then maybe hits like a 20. Okay. Then second person comes up, and on their dartboard, they hit 20, and then they hit a 20, and then they hit a 20, right? So the difference is accuracy is how well you can get to the true value. So if we are assuming that the bullseye is the true value here, person number one actually had better accuracy because they got the bullseye. Person number two didn't get the bullseye. So accuracy, let's assume that that's what they were going for, right? They didn't get the accuracy. So because they never got the bullseye. Precision is how well you can do it over and over and over and over again. So the second person that came in and hit the 20, hit the 20, hit the 20, I think that's called cricket, right? Or whatever. They'd be really good at that game, right? Because they just got all three 20s. That's great precision, but they never got the bullseye. So that's not as good in terms of accuracy. So they always use that as an example. I'm not sure it's a great example. So I like data. So let's look at data. So I've got two groups of students and I gave them a sample of aluminum. I said, okay, I want you to do 3 trials. Tell me the density of the aluminum. So they take their mass and volume measurements. Group A got a density of aluminum of 2.63, 2.62, 2.63. So that's trial 1, 2, and 3. Group B comes along. They've got 2.55, 2.85, 2.70. Just looking at that alone, you can definitely see that Group A had better precision. Those results are nice, tight, narrow range in great agreement. That's like the throw in the 20, the 20, the 20, right? They got the same answer basically every time. And so that's very good precision. When you look at Group B, doesn't look so great in terms of precision. Now, how do we evaluate accuracy? If we're doing multiple trials, and we'll do this in the lab, I'll have you calculate an average. And then I'm going to ask you, okay, well, how well does your average agree to the known value? So I know this may seem kind of strange, but Group A, even though their precision was great, their average that they got for the density of aluminum was 2.63. Group B, their answers were kind of all over the place, but the average for their density was 2.70. If I know that the true density of aluminum is 2.70, although it seems a little strange, B actually had better accuracy, but it's only because the average that they got matched the true value of the density for the aluminum. And because of that, Group B had better accuracy. All right, so that's really the difference between precision and accuracy. So in Intro Chem in lab, we typically did 1 trial, and I was just basically happy if you understood the calculations and what the numbers meant. In Chem 1, a lot of times now we're going to do 2 trials, and we're going to be looking at both precision and accuracy. So if your trial 1 and your trial 2, your answers are really close together, that's going to tell me you had really good precision. It may not match the known value, but it at least shows me that you can repeat your process. All right. So based on this data set, which group had better precision? Group A, better precision. All right. And that's because their results, they pretty much match, but they're in a very narrow range of date, right? It's a very narrow range of answers. They only had 2.62, 2.63, 2.63. Group B, their precision was pretty poor comparatively. It went from 2.55 to 2.85, but their accuracy was better because their average that they got for the density of aluminum, it matched the known density for aluminum. So their average matches the known. All right, so that's how we really look at precision versus accuracy. All right, in terms of data collection. Okay, so that's another thing to think about in terms of data, what your data tells you. Then the last thing we've got to talk about in the chapter is unit conversion. So this is where we started, where it's like, okay, we're not on the standard system. We're not on the metric system. We have our English units. We need to get on the metric system. So we're going to have to know some conversions. So I had mentioned about the prefixes that you needed to memorize. There are a few conversion factors I also need you to memorize. It's just these 4. We've obviously got tons of conversion factors, but these are the ones I need you to know. Anything else I'll give you. We need one for length. which is 1.1 inch is 2.54 centimeters. We need one for mass. 1 kilogram is 2.205 pounds. Or you can remember 454 grams in a pound, something like that. But you got to remember one of those. That a gallon is 3.785 liters. All right. And then for volume, remember that a milliliter and a cubic centimeter are identical. Now, if you notice on these, I wrote it out as 1.000 milliliters is 1.000 cubic centimeters. The zeros there, we don't need them. I would probably just write this as 1 milliliter is 1 cubic centimeter. I just wanted you to understand that these conversions are exact values. So they're not going to limit sig figs in our calculations. Okay, so the sig figs for our answers are going to come from the measurement, and these aren't measurements, they're conversion factors. So I'll explain what I mean here in just a minute. So the chemist's way of converting units, which is also going to be the chemist's way of doing stoichiometry problems, that methodology is called dimensional analysis. So the way dimensional analysis works is we start here looking at unit conversions, and then later we're going to look at it in terms of chemistry calculations. So we're going to learn the process. And I like this process. It's very logical. So I always thought this was just a great way to solve problems. It's basically a neat way of doing ratios. So an example here is, let's say I've got 76.3 millimeters and I want to convert that to meters. What I notice here is I've got the base unit of meter. The only thing that's changed is I've got the prefix. So all I need for this is to remember that prefix of milli. All right, so in this case, millimeter is equal to 10 to the negative 3 meters, right? The meter is just the base unit. The milli is equal to 10 to the negative 3. Now, if you in intro, if instead you remembered it as 1,000 millimeters is equal to a meter, that's going to work just as well. All right. The textbook way, Tro, what he does is let's just remember the prefix and swap it with the exponent that we have listed. And that it's the same. So what I'm going to do here is I'm going to start with the number that's given, 76.3 millimeters. Conversion factor on the bottom needs to have the unit of millimeters so I can cancel out my unit. And then I'm looking to solve for meters, so meters goes on top. So the Tro way, the new way, is to put 1 millimeter and then 10 to the negative 3rd meter on top. So the millimeter, the milli prefix, you just replace it with 10 to the negative 3. Okay, that's the new Tro way. So 1 millimeter is 10 to the negative 3 meters. Or if you want, on the bottom, you could have put 1,000 milliliters is equal to 1 meter. It's the same thing. It's just you're multiplying both top and bottom by 1,000. But it's the same conversion factor. So again, the Tro way is to, whatever the prefix is, you put 1 with the prefix, and then you, on the other side, you replace the prefix with the correct exponent. So going back to that sheet, right, milli is 10 to the negative 3rd. So all we're doing here is replacing milli with 10 to the negative 3rd. So then we're going to take 76.3, which we started with, multiply it by 10 to the negative 3rd, and we end up with 0.0763 meters. Okay, so let's try another one. We've got 0.556 kilometers, and we want to convert that to feet. And I got us started. I gave us the, well, I got the conversion from feet to inches, just in case we don't know. So first thing is, if I look at my list of conversions to memorize, what are we going to need here? I see that an inch is equal to 2.54 centimeters. Kilometers, I could get to centimeters just using the prefixes that I know. And then from inches, I could go to feet. So I'm going to make like a little flow chart. I'm going to take kilometers and convert it to meters because that's just a prefix. Then I'm going to take meters to centimeters because, again, that's just a prefix. And the reason why I'm doing that is because I know how to get centimeters to inches because that's in my memory bank. And then from there, I can get inches to feet with the conversion I gave you here. All right, so I'm going to start with 0.556 kilometers. First prefix, kilometer on the bottom, meter on the top. Again, the TRO way, the new way, is to put 1 with the prefix and then replace whatever that prefix is with the proper exponent. So the one that we learned, right, kilo is 10 to the third. So 1 kilometer on the bottom, 10 to the third meter on top. Next conversion, we are going to get rid of meters on the bottom and we're going to go to centimeters. And again, the same idea, wherever the prefix is, we put the 1. And then centi is 10 to the negative 2. So we're going to have 10 to the negative 2 on the bottom. So 1 centimeter is 10 to the negative 2 meters. If you remember from intro that there's 100 centimeters in a meter, that works just as well. Next conversion, we're going to get rid of centimeters and go to inches. This is one of the 4 that we need to memorize. 1 inch is 2.54 centimeters. And then the last one here, we're going to get rid of inches on the bottom and go to feet. And that conversion I gave you is that there's 12 inches in a foot. So the dimensional analysis way is start with what you're given in the problem, set up your conversion factors so that your units cancel as you go. So kilometers on top, canceling with kilometers on the bottom. Meter on top, canceling with meter on the bottom. Centimeter on top, canceling with centimeter on the bottom, right? Inches on top, canceling with inches on the bottom. So if that's working, it's a really good sign that you did this right. When I go to solve, all I'm going to do is anything that's on the top is going to get multiplied. Anything on the bottom, I'm going to divide. Now, in terms of entering in the exponent, if you want, you can think of 10 to the third as 1,000. So you're going to multiply 0.556 times 1,000. If you want to type it in as you see it, you might want to type it in kind of like this way, 1 times 10 to the third, or 1 times 10 to the negative 2. Now, I like my EE key. So my EE key is my exponent key. And that is that exponent there. Okay, so I'm going to take 0.556, all right, and then I'm going to multiply it by 1 EE3. That's my 1 times 10 to the 3. All right. Then I'm going to divide that, because it's on the bottom, by 1 EE negative 2. Okay. Then if I keep going, I'm going to divide that by 2.54 because it's on the bottom. And then the last thing I'm going to do is divide that by 12 because it's on the bottom. Now the answer I get, 1824.147. We don't need anything past that. So let's just look at that. All right. That is my answer in feet. Now we got to talk about significant figures. So if we go back to the conversions and start looking at sig figs, we really don't want to do that because the 1 is an exact 1, doesn't limit sig figs. We're not going to worry about the conversions. It's exactly 12 inches in a foot. Remember that what the reason why we look at sig figs is because we want our answer to not only be obviously accurate, but we want to show how well we knew that measurement. So our measurement only had 3 sig figs. So our answer can only have 3 sig figs. So we always look at the measurement, not the constants or the conversion factor. It's just the measurements that we want to look at. So 1824, I would take the 1, 8, and the 2. Those would be my 3 digits, my 3 sig figs. The 4, I'm going to replace that with a 0 just for magnitude, right? Because if I write this as 1824, I've got 4 sig figs, so that's not right. So what I do is I take my 1, 8, 2, and then replace the 4 with a 0. As long as I leave the decimal off, that only has 3 sig figs. And then I just put in my unit of feet. So 1,820 feet. Again, some textbooks are like, let's just use scientific notation. So 1.82 times 10 to the third feet would also work. All right, so depending on, I'll take either one. Both of those are perfectly fine. All right, so that's how we work dimensional analysis. We're going to try another one here. This one's an example. It's a little bit harder only because it's got an area unit rather than just a length. What you'll notice is I've got 476 centimeters squared. So the squared unit, it makes a difference, right? It's an area, it's a length and a height multiplied together. So I want to convert this centimeter squared measurement to inches squared. Now, the conversion that I know from my memory bank, which is 1 inch is 2.54 centimeters, that's only good for one dimension, and I need it to work for 2 dimensions. So the good thing is that what I do is if my measurement, my unit conversion for length is 1 inch is 2.54 centimeters. If I'm going to use it for area, I'm going to take that 1 inch is 2.54 centimeters and I'm going to square it. Basically, I need to do it twice because I need to do this for the length and the height. So I square everything in the parentheses. The 1 becomes a 1 because 1 times 1 is 1. Inches squared. Then the 2.54 squared becomes 6.45 and centimeters squared. So I just took a one-dimensional length conversion and changed it to a two-dimensional area conversion, right? And let the units tell you, right? If this is squared, then you know you've got to square it. So we're going to try one on the next page. Okay, so on the next page, I've got 1.56 times 10 to the 4th inches cubed, and I want to convert it to meters cubed. So what conversions am I going to need here? Well, I know that there's 1 inch equal to 2.54 centimeters. And then I'm thinking, okay, how does centi relate to meters? Remember, I know that 1 centimeter is 10 to the negative 2 meters. Now, again, these are one-dimensional. These are just for the length, one dimension. What I've got here is volume units. I've got cubed, right? Length, width, and height. So what I'm going to do is I'm going to cube everything in that parenthesis, in that conversion. So 1 cubed becomes 1. Inches cubed. 2.54 cubed is 16.387, which you can keep at that or just go 16.4 if you want. Then the centimeters to meters, if I cube that, 1 times 1 times 1 is 1 centimeters cubed. Okay, 10 to the negative 2 cubed is 10 to the negative 6, and that would be meters cubed. Okay, so all you have to do if you've got a one-dimensional unit and you need to make it either a two-dimensional or three-dimensional, the units will tell you. We're just going to have to cube it to make it a volume conversion, or we'll have to square it to make it an area conversion. Okay, so now I've got the conversions I need to solve this question. All right, so I have 1.56 times 10 to the 4th inches cubed. All right, on my conversion factor, I know I need inches cubed on the bottom to go away. We decided to go to centimeters cubed first. All right, the conversion tells me that 1 cubic inch, so 1 goes on the bottom with cubic inch, is equal to, remember this line here in your conversion factor, that's an equivalence line. It's telling you that the top and bottom are equal. So 1 inch cubed is equal to 16.4 cubic centimeters. All right, so anything in parentheses, numerator, denominator, with that line in between, that is telling you that those two are equal. All right, and then in the next conversion, we're going to get rid of centimeters cubed and we're going to go to meters cubed. So our conversion was 1 cubic centimeter is equal to 10 to the negative 6 meters cubed. So on my calculator, all right, I'm going to just show you real quick. I'm going to take 1.56 times 10 to the 4. So I use the EE key 4 times 16.4. All right. And then I'm going to be multiplying by 1 times 10 to the negative 6. My answer is 0.25584. My starting measurement has 3 significant figures. So I want my answer to also have 3 sig figs. So I'm going to go 0.256 because we're cutting off the 8, so the 5 needs to round up. So my answer here, 0.256 meters cubed. All right. Okay, then the last one here, well, second to last one, we've got 2 units. We've got like a force, pounds per square inch. We want it kilogram per meter squared. So we're going to have 2 things that we got to do here. I like to write things with 2 units this way. So instead of pounds per square inch, I'm going to say 14.70 pounds is equal to, right? Because that line is just like that slash. It's an equivalence line. And that's equal to 1 squared inch. So writing 4.70 pounds per inch squared is the same as writing 4.70 pounds over 1 inch squared. And what I need to do is convert my pound unit to kilograms. And then I'm going to have to convert inches squared to meter squared. So I've got 2 things I got to do here. Let's do the mass measurement first. So first one is, let's get rid of pounds and go to kilograms. So in your memory bank, you want to remember that a kilogram is 2.205 pounds. What I remember to help me remember what goes where. A lot of students remember the 2.205, they just put it in the wrong place. So I don't know, this helped me. I always remembered that pounds is the bigger number. So 2.205 pounds per kilogram. All right. So what I've done in this first conversion is I got rid of pounds and I converted to kilograms. So I've got that first, I got my numerator done. I've got kilograms, that's what I want. So now the second conversion, this is going to look a little strange, but I'm going to ignore my first conversion. And now I'm going to look at my denominator. Inches squared, I need to cancel out in the numerator. And I'm going to try to go to meters squared, but I can't quite do it immediately. I've got to go to centimeters squared first. And then from there, I can go centimeter squared to meter squared. So the inch to centimeter conversion, right? 1 inch is 2.54 centimeters. So if I square that, 1 squared inch, 2.54 squared is that 6.45 that we saw earlier. And then in the next conversion, 1 centimeter squared, 1 centimeter is 10 to the negative 2 meters. So a squared centimeter is 10 to the negative 4 square meters. 10 to the negative 2 times 10 to the negative 2. All right. So on my calculator, all right, if I look, inches squared now cancels out with inches squared. Centimeter squared cancels out. And the 2 units I'm left with are kilogram per meter squared. So I'm going to take my 14.70, divide it by 2.205, divide it by 6.45, and then divide that by 1 times 10 to the negative 4. So I got 10,335. My starting measurement here has 4 significant figures, right? The 14.70 has 4 sig figs. Oh, let's focus. Focus, focus, focus. There we go. So my answer, the 10,335, 4 sig figs, we're going to take 1, 0, 3, 3. We're stopping there so that 5 becomes a 0. But because we're cutting off the 5, that previous 3 has to go up to a 4. So this would be 10,340. And the unit was kilogram per meter squared. So again, we took 1,0,3,4,0. 0, just the placeholder to show the magnitude. But there's my 1, 2, 3, 4 sig figs. All right. So there's my 4 sig fig answer. Sorry about that. Someone came to the door. So we have 4 significant figures for our converted force. All right. Last one here before we start talking about temperature. This one's a little bit different. It says, what is the volume in gallons of 10.0 kilograms of methanol. Density is given 0.790 grams per milliliter. That's going to act as a conversion factor. All right. When you have that gram per milliliter, like we were talking about up here, what this means is we have 0.791 grams equal to 1 milliliter. That per, that's an equivalence line. So there's your equal sign. All right, so that's going to be a conversion factor to get us between mass and volume. Now it says, what would be the volume in gallons of 10 kilograms of methanol? So we're starting with 10.0 kilograms, and we're trying to figure out how many gallons this will be. All right, so first thing we do is when I look at my density, I notice that the mass unit and density is in grams. All right, and this is going to be my only way to get to volume is to pass through density. So I've got 10.0 kilograms, and I need to convert that to grams. So I have 10.0 kilograms. 1 kilogram is 10 to the third grams, or 1,000 grams. Next conversion, this is where the density is going to come in. We're going to convert grams to milliliters using that given density. And the way that it's written, it says we've got 0.791 grams is equal to 1 milliliter. Okay, so that's the density that was given to us in the question. That's what I highlighted above. Now from there, my job is to get from milliliters to gallons. Now, how do we get gallons? The memory bank, we have a conversion from liters to gallon. I've got milliliters here, so I'm going to just convert milliliters to liters. Again, what we did in intro is we would have put 1,000 milliliters on the bottom, 1 liter on top. Perfectly fine if you want to do that. The neutral way is to say, okay, put 1 with the prefix, and then let's put the appropriate power. So milli is 10 to the negative 3. So 1 times 10 to the negative 3 liters. It's the same though. If you put a 1 on top and 1,000 on the bottom, it's exactly the same. So do whichever one you like better. Last one is 1 gallon is 3.785 liters. And I'm getting that from that memory bank. So I do want you to remember that one. The gallon is 3.785 liters. Okay, and that'll get us from the 10 kilogram mass into gallons. So 10 kilograms is really 10,000 grams. If I divide that by the density, that'll tell me the volume that 10 kilograms of methanol would occupy. But then changing milliliters to liters, dividing by 1,000, right? And then the last thing is we've got liters going into gallons. So we're going to divide by 3.785. All right, now we of course go back, we got our answer, but we have to say, well, how well do we know that answer? 10.0 has 3 sig figs. So our answer here can only be 3 sig figs. So if I look here, I'm going to take 3.34. That would be my 3 sig figs, and my unit would be gallons. All right. Okay, so we did our unit conversions. The very last thing we got to look at is temperature. We had these in intro, so you're probably familiar with these. We have our 3 temperature scales. Do not ask me why we still use Fahrenheit, because it doesn't make much sense to me. We've got Fahrenheit came first, right? So his scale seems a little odd. He, I think, kind of picked the body temperature. I've heard either of a dog, then I heard maybe it was a human, but he picked that to be the kind of the 100 mark. So that's 100 Fahrenheit body temperature of a dog. All right. And then this like saltwater solution was the 0. It doesn't really make a whole lot of sense, but Celsius came along later and said, wait a minute, let's just use water because everybody's got water. Let's make the freezing point of water 0, the boiling point 100, bam, standard. Kelvin came along later and said, yeah, that works really well, but let's make a system where we can't have negative temperatures. So we have to, if we think that temperature is a measure of molecular movement, then we shouldn't be able to have negative temperatures, right? Because you can't have negative movement, right? So instead, we're going to have this scale where there is an absolute zero. So at zero, that means molecules no longer move and temperatures will only be positive. So it turns out the Celsius scale is very good. It's a 1-to-1 correlation with Kelvin. So basically, if I go up 1 degree Celsius, I also go up 1 Kelvin. So the Celsius to Kelvin, you take your Celsius temperature and you add 273.15. All right. Then the Fahrenheit Celsius is a little bit different. It's not quite as simple. So you want to memorize one of those two formulas. It's the same formula. I've just changed it to whether you have Celsius and you're getting Fahrenheit, or if you have Fahrenheit and you're getting Celsius. But no matter what temperature conversion you do, and you do want to memorize these, so let me highlight, right? You do want to memorize those conversion factors for the test. What you do is with any temperature conversion, doesn't matter which formula you're using, follow the decimal place of the original temperature. So when you do the conversion, always follow the decimal place of the original temperature. So this first example, I've got 85 Celsius and I want to convert it to Fahrenheit. 85 only goes to the ones place, so my answer is going to go to the ones place. So I take my Celsius, 185, formula says first multiply it by 1.8, add 32. The 1.8 and the 32, those are exact numbers, so they have nothing to do with the sig figs or the decimal places. All we have to do is look at the original that's given to us in terms of the decimal place and keep that same decimal place for the answer. So we gained a sig fig here, but that's actually okay. So just plug in this in so you can see. If I take 1.8 times 85 and then add 32, that's where we're getting 185 from. Next one is we've got Celsius and we want to convert it to Kelvin. So we take the 335 Celsius, and that formula says we're going to add 273.15. So calculator, when I add those together, I get 608.15. But remember, I'm going to keep the decimal place of the original. So I'm going to round this to the ones place. So my answer here is going to be 608 Kelvin. All right, if you're wondering, the Fahrenheit has a degree symbol, Celsius has a degree symbol, Kelvin does not. It's just a unit by itself, like grams or kilograms, no degree symbol. Last one here is Fahrenheit to Kelvin. And unfortunately with that, you've got to go to Celsius first. There's no direct formula from Fahrenheit to Kelvin. So if we know Fahrenheit, we're going to take that negative 20.8 and we're first going to subtract 32. And then we're going to divide by 1.8. You got to be a little bit careful for this one on the calculator, and I'll show you what I mean. If I take negative 20.8 minus 32 divided by 1.8, the calculator follows order of operations. And it divides the 32 divided by 1.8 first, and then it does the subtraction. We don't want that. We've got these parentheses. So we got to do the parentheses first. So you got to take the 20.8 negative minus the 32, hit enter, all right, and then divide by 1.8, and that'll get you your answer. Or if you want to use parentheses, just like it's written, do that. Parentheses 20.8 negative minus 32 into parentheses, then divide by 1.8. All right, and that's where we get that answer of negative 29.3 Celsius. All right, and we went to the tens place because that's what we had on the Fahrenheit temperature. Now that we can add the 273.15 to go to Kelvin. So I'll just keep that answer, or you can round it, doesn't matter, 29.3 added to 273.15. So calculator here gives me 243.85. But again, we need to go to the tens place. So we're going to round that to 243.9 for the Kelvin temperature. Okay. So in terms of memorizing, right, for this first chapter, there's a couple things. Obviously, your definitions, you want to know those, but you've got to memorize those 6 prefixes and you've got to memorize those 4 conversion factors. And then you need to memorize those 2 temperature formulas. All right. And that will be everything you need to have memorized for the first chapter. So what you have in the first chapter for your homework, you want to do the TRO homework that you'll see listed in the chapter 1 notes posted in my courses. In fact, let me just share my screen so I can show you what I'm talking about. So when you go into the chapter 1 folder, all right, chapter 1 folder, scrolling down. Okay, the chapter 1 notes, we showed this on Tuesday right there. These are the notes I use for class every day. These are those suggested homework problems in TRO that's on the Pearson site. So you want to do these as practice. Then if you want to check your answers, this is my answer key where I've done all the problems and you can look to see how I did it. If you got anything wrong, you can reach out to me. We'll do a Zoom session to go over it. Then this is where I post the videos for the notes. So today's video part 2 will be posted later tonight. More videos where I just broke up the topics into smaller segments. Couple of times, like sometimes I'll go over specific homework problems that I think are really good. So make sure you watch those. So these are conversion factors and sig figs. Then I gave an extra worksheet for some more practice. So the TRO homework, the worksheet, those are very good for you to practice. The more practice, the better. And then you've got your practice quiz 1A, 1B, 1C. Remember, the practice quizzes you can take as many times as you want. All right, but they are going to help get you ready for the credit quiz. Now, the credit quiz is due Thursday at midnight. Normally, again, like I said at the beginning, the practice quizzes are open till the end of the semester, but just because of attendance, practice quiz 1A is going to be due Sunday at midnight. So just make sure you get something submitted by Sunday at midnight so that you don't get dropped from the class. All right, so everything that you need to complete chapter 1 is in the chapter 1 folder. Just in case anybody missed on Tuesday, the textbook, those homework problems that are in TRO, you'll find those up here. You go to the first day course materials. All right, scroll down. This is the link to your book. And then when you open that up, you have a few more clicks that you got to do. You want to launch the courseware. If anybody has any problems with this, you want to walk me through it again, I'll be happy to do that. Then you open up the book. And then once that happens, you get your Pearson ebook. Okay, so we got another click. Yes, open the book. 6 clicks later, we open the book, and then this is when we'll find our first chapter. And those homework questions that I had mentioned, if we scroll over here to the table of contents and we pull up chapter 1. Why isn't it coming up? Oh, it's just thinking. I'm sorry. I was being impatient. It's spinning. There we go. So click on chapter 1, open that up, and then go to the end of the chapter, just like you would if you actually had the textbook. And then there's your exercises. Those are the homework problems that I suggest doing. Not all of them, just the ones that I numbered back in the notes. All right. So if you have any questions this first week, just kind of getting used to everything, please let me know. But remember, for homework to practice this weekend, the homework that's in TRO that I just showed you, the extra worksheet, then you've got practice quiz, 1A, 1B, and 1C, and then do all of that and then take the credit quiz. And the credit quiz again is due Thursday, 8/22 at midnight. All right, and that'll get you, like this will give you lots of good practice for chapter 1. Credit quiz 1, I'll get it graded. So it's due next Thursday. I'll get it graded the following Friday. And then that'll kind of see how you started the semester. But over the next week, if you have any questions on chapter 1, please reach out. I'm here to help. And then on Tuesday, when I see you again, we will be looking at chapter 2. So I wish you a really great weekend and I'll see you back on Tuesday.